Hi class, welcome back. We're gonna continue our discussion of Mars today. So last time we met, we chatted about how we became interested in Mars as a species, a planet other than our own. We talked a little bit about the spacecraft that we've sent to Mars. And so what we're gonna do today is we're gonna talk about two things. We're gonna talk about the physical character of Mars, the kind of nature of the places that we've discovered there. And then we're going to talk about the weather and the climate, and in particular, the volatiles, water, and the search for water there. That'll set the stage for our discussion next class, which will be the search for life on Mars and the things that we've done and what we think and what we're looking for. Okay? So in the picture behind me today, this is probably my favorite place on Mars. This is called Noctis Labyrinth, or the Labyrinth of Night. It was one of the first places that Mariner 9 sent images back to Earth of. It was something we had never seen until we sent a spacecraft to Mars. It's a vast network of really deep, steep-sided canyons. It's just one of the coolest looking places you've ever seen pictures of. And there's lots of pictures of this area now from spacecraft that we've sent over the years, but it's one of my favorite places on Mars. And we'll come back to this a little bit later when we talk about the surface. Okay, so let me go ahead and start a few slides. So the thing to remember always with all of our studies is that for any topic that you and I spend just a single lecture talking about, we could spend an entire year talking about. We know so much about Mars at this point because we have spent decades looking at it through telescopes, sending spacecraft there to explore, and it's a big planet. The total surface area of Mars is about the same as the surface area of the land on the Earth. So it's a very extensive planet. We certainly haven't been every place on the surface. We've mapped the entire planet from orbit, but there's a lot about this place that we know, and you and I can't possibly discuss all the things about Mars that we do know. So we're going to just take a global view today. We'll tell you about some of the high points. So I'll describe the kind of big famous features of Mars, the things that you may have heard about if you've studied Mars before, the things that you'll encounter if you go watch movies about Mars, either science fiction movies or documentaries about Mars, or if you read books about Mars, the kind of big features of the things that you'll hear about. And so throughout this, you'll see and you'll encounter some familiar things, but we'll also point out some unusual things. And not unusual in the sense necessarily that we don't know what we're looking at, but unusual in the sense that we saw them on Mars unexpectedly, or it caught us by surprise, and they're potentially very interesting things that can help us learn a lot more about the planet. And then we're setting the stage to talk about climate. So that's where we're really headed, and we'll do that in the second half of the lecture today. So the kind of major features of Mars you can glean from a single global image of the planet. These global images are ones that our spacecraft are very good at these days. And so we have just exquisite high resolution pictures, not unlike this one that I'm showing you here. And so when you look at the planet in this view, the North Pole is near the top and is kind of tipped towards you. So you're kind of looking at the northern hemisphere with the southern hemisphere down there on the bottom. You'll notice that Mars, like the moon, has both highland and lowland terrain. So in Mars in particular, the northern hemisphere is lowland terrain, and we'll look at the topographic map here in a minute, and the southern hemisphere is highland terrain. Roughly speaking, that corresponds to younger terrain in the north and older terrain in the south. That's something about Mars's geologic history that we're still trying to understand. There are craters on the surface of Mars. So Mars does have atmosphere like Earth. It does have weather, which geologically can erase features, but there are definitely impact craters. So if you look on the right side of this image near the limb of the planet there, in between the kind of dark areas, you'll see some kind of freckles on the surface of the planet. Those are all impact craters. There's definitely polar ice caps. You can see the polar ice cap here in this image. The Valles Marineris, so this is the largest canyon in the solar system. We'll talk about it at great length, but it stretches kind of across the lower center of the image there from left to right. If you put the United States on that canyon, the canyon would stretch from San Francisco to Washington, D.C. So it's an extremely long canyon system. And then Mars also has enormous volcanoes. It has the largest volcanoes in the solar system. So we've encountered other volcanoes in the solar system, both the sulfur volcanoes on Io, as well as the cryovolcanoes on Enceladus. But if you look here on this global image of Mars, you'll see these kind of three large circles on the left side of the image in a kind of diagonal line. Those are the Tharsis volcanoes, and they are the largest volcanoes in the solar system. Okay, so we'll talk about all of these global features in turn here during this part of the lecture today. So this is a global elevation map of Mars, and if you go look for this online, I'm sorry I didn't put the link here on the slide, but I'll add it before I post the slides to the class website. But you can get this global elevation map from NASA. It's a huge file, but it'll allow you to zoom in and look at all the various areas of Mars at really exquisite detail. If you go to the mars.google.com site, that's the base, this base image is part of their map there that you see. So what you see here is the topographic representation of Mars. Mars does not have a standing ocean, so there is no sea level. And so we pick a reference altitude for Mars to represent sea level. It's some average altitude that goes completely around the planet. And that's roughly the boundary between the yellow and the green anywhere that you see. You can think of that as sea level on Mars. And so then anything that is green or blue on this picture is below that quote unquote sea level, that reference altitude. And anything that is orange or red or brown or white is above that sea level. And so what you see is that Mars has a very low northern hemisphere. The entire northern hemisphere is blue, and a high southern hemisphere. And so that is that highland-lowland separation that we just said. The average separation in altitude between the highlands and the lowlands is about 8 kilometers. Northern hemisphere is roughly 4 kilometers below the average. The southern hemisphere is roughly 4 kilometers above the average. There is a notable, very deep spot there in the southern hemisphere that is called the Hellas Basin. It is an impact feature. It's an enormous impact crater. The lowest point on Mars is in Hellas Basin. It's actually not the basin itself. There's a small crater in the northern side of the Hellas Basin there. Here I marked these, the northern side of the Hellas Basin there, and that low point is 8,200 meters below the reference altitude on Mars. The highest point on Mars is Olympus Mons. It's the largest volcano in the solar system, which we'll talk about in a few minutes. It's over there on the left side of the image, and the peak of Olympus Mons is 21,229 meters above the Mars reference altitude. Okay? So let's zoom in for a minute just on this region of the planet. This is far and away one of the most interesting regions, and it contains some of the things that we're going to look at today. So this region, the red area is usually called the Tharsis bulge or the Tharsis shield. So this is the highest point on Mars. Curiously, it is exactly across the planet from the Hellas Basin. We'll talk about that in a few minutes. But you'll see there the 3 Tharsis volcanoes standing up on the top of the Tharsis bulge. You'll see Olympus Mons on the edge of the Tharsis bulge there. And then the Valles Marineris stretches across the southern part of the Tharsis bulge there, and all that intricate web work on the left end of the Valles Marineris, that's Noctis Labyrinth. Okay? So I want to zoom in on this part. Of all the places on Mars that you may or may not be familiar with, this is one that some of you may know about, and you may not know that you know about it, and that's because this is the region of Mars that is the setting for The Martian. So when Andy Weir wrote The Martian, he definitely picked real places on Mars. He tried to stay as true in many ways as he could to what the real science was, which is why The Martian is such a great movie. If you haven't watched it, you should totally go watch it. Those of you who have seen it, you know that Mark Watney does some traveling on Mars. And so this shows up there at the top where the station that Mark Watney was at is located on Acidalia Planitia. It shows his journey to the landing site there at the south, and then his journey to the Schiaparelli crater there as well. Okay, so this is one of the ways that we talked about last time that Mars, real Mars science, has kind of pervaded popular culture, and the movie The Martian and the novel The Martian, for those of you who have read it, is just kind of one modern example of that. Okay. Okay, so let's talk about some of the global features then. So far and away, one of the easiest global features on Mars that you can see from Earth, if you wait for Mars opposition each year, you go out in your backyard and you look at Mars through a telescope, you can very often, if the scene's good, see the polar ice caps. And so this is a picture of both the North Polar Ice Cap and the South Polar Ice Cap. So these are permanent ice caps on Mars, just like the Earth, at least for the moment, has permanent ice caps. Mars also has permanent ice caps. They're largely water ice, and then they have a thick layer of CO2 ice, dry ice, on top of them. Oh shoot, I don't remember the value. I'd have to look in my notes. Look in the notes, and I have the thickness of that CO2 layer written down. Seasonally, the ice caps do grow and shrink, and that's largely associated with the fact that the dry ice is volatile. And so it readily evaporates into the air and then readily freezes out of the air directly into ice as the temperature fluctuates between the summer months and the winter months on Mars. And so here is a picture from NASA of the North Polar Cap, both in the summer on the left and in the winter on the right. And you can see how that CO2 dry ice builds up and kind of makes the polar ice cap look a lot bigger. And then during the summer, it evaporates back away. And then you see just the permanent ice cap there behind it. Now, the Mars, as we said last time, is tipped with regard to the sun, just like the Earth. So it has seasons. So when it's summer in the northern hemisphere, it's winter in the southern hemisphere, just like it is on Earth. And so when the northern ice cap is shrinking, all the CO2 dry ice on it is evaporating into the atmosphere. That CO2 is being transported through the atmosphere, and it condenses and freezes onto the southern ice cap. And then during the southern winter, when the south pole of Mars is exposed to the sun, it evaporates there and transports to the north and builds up the northern ice cap. So there's this kind of transport of the CO2 through the Martian atmosphere, okay? One of the other great features on Mars is the Mariner Valley. So this was named after Mariner spacecraft because they were the first spacecraft to photograph it. Of all the things that Percival Lowell saw on Mars that he thought were canals, this is literally the only thing that corresponds to anything. If you look at his maps, there are always dark streaks that roughly correspond to where the Mariner Valley should have been, or where the Mariner Valley is. Okay, so it is a large canyon. It stretches about 5,000 miles. It's about 3 times as deep as Mount Everest is tall, and it's many thousands of miles across. So the Grand Canyon of Earth, for those of you who have been to the Grand Canyon, could fit off in one of the little side canyons that you see pulling off of the Mariner Valley here. So the real question about the Mariner Valley is, holy smokes, how do you make a canyon that big? And as it turns out, it is not a feature that was formed by erosion. Erosion certainly affects it, and it certainly has influenced it along the edges. If you blow this picture up and you look at the edges, you'll certainly see things that look like erosion features leading into the Mariner Valley. We'll talk about that when we talk about water in the next little bit of the lecture. But the canyon itself had to somehow form. And so we think it's a tectonic feature. So Mars doesn't have plate tectonics, but the planet, like all the planets, used to have a hot surface. And when it cooled and became the crust of Mars, we think that surface cracked. Okay, and that crack became the Mariner Valley. So that's one of the processes that we think led to this. So this is kind of like the rift valleys we see on Earth, where the plates of the Earth are pulling apart. Okay, so that's basically what happened with the crust of Mars, except it doesn't have plates, and so the surface is shrinking as it cools, and so it pulls apart and made this fissure. Now, that may sound unusual to you, but I'll remind you that many of you have encountered this before. Okay, and so the most famous example is when you bake a pumpkin pie. And I didn't even have to search very hard to find a pumpkin pie that looked exactly like the Mariner Valley. So a pumpkin pie, when it's hot, it's completely smooth and it fills the crust here. But as the pie filling cools, it shrinks and it pulls apart and it makes these deep fissured canyons, not unlike the Mariner Valley. Okay, so this is kind of one of the primary ideas we have for how the Mariner Valley formed. And someday we'll send real geologists to Mars, and we'll spend a lot of time down in the canyon, and we'll try and figure out what the story is. But right now, the best models we have suggest this is the mechanism. Now, Mariner Valley is quite large, and so now that we have really good altitude data from our satellites orbiting Mars, we can make really nice three-dimensional models of Mars. And so here's a movie of what a flight down the Mariner Valley would actually be like. And so I put the link to the NASA video there for those of you who would like to go watch it again. But let me go ahead and play it here. It has an audio track. I'll let the NASA narrator talk you through it.
Lifting off in a cloud of dust, our scout ship heads for Mariner Valley. A swarm of tornado-like dust devils whirls across the mesa, just as in the deserts on Earth. Dodging them, we pass impact craters, where large meteorites violently struck long ago. Dead ahead in our race toward the rim, winds are blowing dust clouds up the valley slopes. Mariner Valley is 10 times longer, 5 times deeper, and 20 times wider than Earth's Grand Canyon. You could drop the entire Los Angeles basin inside with room to spare. The rim stands almost as high above the valley floor as Mount Everest on Earth. Looking westward all along the valley's length, we find giant landslides that tumbled off its steep, rugged wall. On the left lie numerous rocky spurs and narrow gullies formed by slumps and avalanches. After crossing a low ridge, we fly up a tributary side canyon. Inside, the canyon twists and turns in a stream-like way. Geologists think this side canyon was born as groundwater escaped and the surface collapsed. Several more tributary canyons cut into the valley's rim. These also grew where groundwater undermined the surface. The valley walls run far into the distance. Its cliffs and ridges were born through earthquake faulting, the main geologic force that began to open the valley billions of years ago. Tucked into the valley's widest part, Melis Chasma, are many layers of dust, sediments, and rock. Each records a slice of time and fills a few pages in the geological record. Ahead lies a catastrophic landslide that crashed down 15,000 feet and shot debris nearly 100 miles across the valley floor. Beyond the landslide lies another basin containing more layered deposits. These offer glimpses of the past and record part of the valley's complex geological story. Farther into the basin, the floor is covered by hills made of layered sediments whose origin remains a puzzle. Winds blowing for millions of years sculpted the soft ground into long ridges. Turning up a narrow canyon and sailing over a gully ridge, we fly into Ophir Chasm and find more sediments, wind-carved ridges, and a steep wall with rock rubble heaped at its foot. A long parade of landslides widened the valley, collapsing walls made of hard volcanic rock. A flight through Mariner Valley gives us an exciting glimpse of its geological complexity. Buried in the rocks of this Grand Canyon of all the planets lies a history book of Mars that scientists have just begun to open. One day, perhaps soon, we'll read the full story of this beautiful and spectacular place.
Okay, so this is a recurring theme that we always have when we visit other worlds, is that being able to see them up close allows us to understand their history. And Mars really is much more that way than any other world, precisely because it has had environmental changes and environmental influences that are not dissimilar to the ones we have on Earth. The evolution of its geology, as well as the weathering that it's experienced over time, the influence of water, wind, all of those things that you heard about in the video. And the real point there is that allows us to bring the kind of deep, great scientific experience we have from those kinds of investigations that we've done here on Earth to bear on Mars. The fact that we've learned a lot about geology already on Earth, we can take that knowledge and transfer it and try and learn something about the history of Mars. Okay? So let's move away from the Mariner Valley and let's talk about the Tharsis bulge. So here are the hemispherical views of the planets with the topological map wrapped around them. And so as you can see here, this is what I told you right at the beginning. Exactly across the planet from the Tharsis bulge is the Hellas Basin. And so one of the ideas that has often been floated around is that the reason Tharsis is bulged out is because of the influence of whatever it was that hit Mars and created the Hellas Basin. We see this kind of effect other places in the solar system. The most prominent place where this is seen is on Mercury. There's a very large impact feature on Mercury called the Caloris Basin. And if you go exactly to the other side of the planet from the Caloris Basin, you see something called the chaotic terrain. And it's this kind of shattered, broken mountain ranges and craters and crustal areas on Mercury. And so this is very similar to that here on Mars. You see Hellas Basin, big, huge impact crater. You go across the planet, and then there's a big bulging part of the planet where something clearly has pushed out. Okay, so on the Tharsis bulge, it is the highest point on Mars, so that's the big red in the elevation map here. And there are 4 large shield volcanoes. So the 3 shield volcanoes in a row there, those are actually on the Tharsis bulge. Olympus, sometimes when you read about it, they'll say it's part of Tharsis, and sometimes they'll say it's not. It's right on the edge of the Tharsis plateau. So, you know, is it there because Tharsis happened? Probably, but, you know, argue with the geologists about whether or not it's part of Tharsis or not. So the 3 volcanoes from north to south are called Ascraeus Mons, Pavonis Mons, and Arcea Mons. They are, like Olympus Mons, all large shield volcanoes. So what shield volcanoes are is when they erupt, they kind of put a layer out on top that layers down over the top of the volcano, and the volcano gets bigger. And then the caldera erupts again, and it puts out another layer, and then it builds up higher and higher and higher. That kind of volcanic activity absolutely can produce layered terrain. And we see lots of layered terrain on Mars, but as we'll argue later, some of that layered terrain, in fact, a lot of that layered terrain we think comes from wind and water processes. But it's important to always keep in the back of your mind when you're looking at any geologic site that the layering could be volcanic in nature. That's particularly important for us because one of the things that we're going to do in the search for life is we're going to follow the water. So we want to know where water has had influence on the planet because that's where we most likely think we could have found life. And if the terrain is layered because of water action, then that's a place where we might look for life or fossilized life. Okay? If the terrain is layered because of volcanic activity, then maybe that's not such a good place to look for life. Okay, so these volcanoes are the largest ones in the solar system. Far and away, the largest is Olympus Mons. So this is one of those digital elevation productions of Olympus Mons here. You can see the caldera at the top. Olympus Mons is the largest volcano in the solar system. It's 3 times the height of Mount Everest. And in fact, so none of these volcanoes are active. Mars appears to be geologically dead as far as volcanoes are concerned. But when Olympus Mons was active, it would, you know, build up in the same way that shield volcanoes do. But at this time, it's so heavy, there's so much material making up Olympus Mons that were it to continue to try to build, it would just press itself down through the crust and into the mantle of Mars. So Olympus Mons is as tall as a volcano can get on the planet Mars. Okay? So those are the volcanoes. We'll talk about them again when we talk about climate in the second half of the lecture today. But I want to tell you about one last odd thing that we've seen on Mars. Okay, so once we have, so this was only recently discovered in the last 10 years or so. There are all these perfect little black circles that we find all over the planet. And so the question is, what do you think those are? Okay, so if we were in class right now, I'd ask a poll for all of you to vote on that. But I'll tell you what NASA thinks they are, is we think they are caves. So these are regions where Mars has been, there are impact craters. Mars used to be volcanically active. And what we think these are great places where either impact craters have punched through into subterranean caverns or where lava caves, lava tubes have collapsed. And so you'll sometimes hear these called skylights. And so these are of extreme interest to us right now because they provide another way to access down below the Martian surface to see what the geologic history of Mars might have been. And so these are a recent discovery just within the last 10 years or so. They're quite interesting. We've never been able to get close to one. We haven't ever sent a rover or lander to one, but there's something there part of the Mars lore now. Okay. So that's just kind of really high level view of all the kind of global geology, global features that you'll see of Mars. As I said, we could have spent days on end talking about all the plains and all the craters and all the mountain ranges and all the weird things that we see on Mars. But that just kind of gives you a global picture. We're going to use that to frame some of our discussion about weather and climate next, and then that'll lead to the search for life on Mars. Okay, so I'll see you for the next half of the lecture. I hope you're all doing well. Take care of yourselves and be safe.